So in this video I am going to solve a problem from H.C. Verma Concepts of Physics. The chapter is Electromagnetic Induction and the question is question number 48. So in the question we have been given a region of uniform magnetic field. The magnetic field goes into the plane of paper. So let this be the region of uniform magnetic field. The cross indicates that the magnetic field goes into the plane of paper and in downward direction. We have also been given a rectangular frame and the frame is being pushed into the region of uniform magnetic field with a constant force. The constant force is F and the breadth is D, and the magnetic field, the uniform magnetic field, has a magnitude B. So we are being asked, let's see what we are being asked. There are three parts to the question. The first part is asking us find the acceleration of the frame when its speed has increased to V. So first of all, let's see what's happening here. If the frame is pushed into the region of the uniform magnetic field, the magnetic flux linked with this frame is going to continuously increase, and therefore an induced EMF will be created in the frame. Because of that, an induced current will start flowing in the frame, and that current will in turn create a force on this arm which will oppose this original force. So they have given that the resistance of the frame is capital R, and we'll see, if we think a little, that the current that flows through this rectangular frame flows in the anti-clockwise direction, like so. If this is pushed in, the flux increases, and because the flux increases, an induced EMF is created, and therefore an induced current is created. The induced current will flow in such a direction so as to oppose its original cause, the cause being this constant force, and therefore the current will flow in the downward direction so as to create another force, let's call that small f, on this arm. The forces on these two arms will actually cancel each other out. So we have to find the acceleration of the frame when the speed is v. So first of all, let us see what the induced EMF is. The induced EMF is given by BLV. So the induced current is induced EMF divided by resistance, and this force is IL cross B. The vector formula for this force is IL cross B, but we already know what the direction is, and because the angle between the current and the magnetic field is 90 degrees, the force will simply become BIL, and if I substitute the expression for I here, I'll get B square L square V all divided by R, and my net equation will be capital F minus this force, which is B squared L squared V by capital R equals mass times acceleration, and we'll get an expression for the acceleration. So the acceleration will be F by M minus B square L square V by mr. So that is our acceleration as a function of the velocity v, or the acceleration when the velocity is v. That was the first part of the question. In the second part, they are saying that show that after some time the frame will move with constant velocity. So when will the frame move with constant velocity? When the acceleration becomes 0. When will the acceleration become 0? When these two terms are equal. So for the second part, we will equate these two forces or these two terms. Let me say that the velocity when the acceleration is 0, let that velocity be v0. So we can easily find an expression for v0. v0 will be Rf divided by b squared L squared. So after some time, when these two forces will become equal, obviously after some time these two forces will have to become equal because V is increasing from 0. So this term was 0 at some time, and as this term increases, this whole term decreases and acceleration decreases, but because still we have a positive acceleration, V will continue to increase, and after some time these two terms will become equal, and when these two terms become equal, A will become 0. So when A becomes 0, the frame attains a constant velocity, and that velocity is given by this. So that is the second part of the question. And in the third part, they are asking us to find the velocity v as a function of time t. So to that end, let me just use this equation, and for a let me substitute dv divided by dt. Let me do that here, dv divided by dt. I'll just take the LCM of these two terms, that's mr, and in the numerator I'll get Rf minus b square L square v. So if I separate my terms, dv divided by Rf minus b square L square v, that will become equal to 1 over mr times dt. I can integrate both sides. The initial velocity is 0, say after time t the velocity is v, and the time increases from 0 to t. So this is obviously the log function. The result of this will be the log function. So I'll get log of Rf, and this is the natural logarithm with base e, minus b square L square v. We will have to divide by the coefficient of v, which is minus b square L square. So let me write the minus on that side. So minus t over mr, and there's a 1 by b square L square here. I still haven't substituted the limits, which are from 0 to v, and I've already substituted the limits here. T minus 0 is just t. So after substituting the limits, I'll get log of Rf minus b square L square v divided by Rf equals to minus b square L square t by mr. Alright, so I'll have to turn the page. I think I'll have to write out that term one more time. So we have log of Rf minus b square L square v by Rf, and that equals what? I think it's minus b square L square t by mr. So that's minus b square L square t divided by mr. So if I exponentiate both sides to get rid of the logarithm, I'll get Rf minus b square L square v equals to Rf times e to the power of minus b square L square t over mr, which will give us v equals to Rf. So I'm bringing the Rf terms to one side, 1 minus e to the power of minus b square L square t over mr, all divided by b square L square. Now let's see. We know the expression for V naught is Rf over B square L square. So this term is actually V naught. So we get V equals to V naught times 1 minus e to the power of minus B square L square T over mr. We also know the expression for F. The expression for F is B square L square V. I don't think we need this. No, I don't think we need this. Let me just, from this equation, I can say that B square L square is Rf by V naught. So for B square L square, let me just substitute Rf by V naught. So I get V equals to V naught times 1 minus e to the power of minus Rf T for B square L square. I am substituting Rf by V naught by mr V naught. So some terms will cancel out, the R terms will definitely cancel out. Yeah, so this is what they are asking us to prove here. So V becomes equals to V naught times 1 minus e to the power of minus Ft by mv naught. So that's the expression for the speed V as a function of the time t. So that ends this video.